Hi, my name is Vinay, and with this experiment we will see how you can control the position of a DC motor with a 20-sim model. So in this experiment we would be using a balancing bot, and we will try to control the position of the DC motor and see how does it works. So I'm using this balancing bot and I'm keeping it upside down, okay, and I've connected to a LAN port and a power cable, and I'm keeping it upside down so to avoid running wildly on the floor. So I will be using the right DC motor, and I will be trying to control the position of the wheel, okay, and using a controller model, okay. So here, this is the model I made. So let's try to understand this. So here I am using a velocity actuator, okay, as a DC motor, and these are the components, okay, which models the entire DC motor setup. So that's a DC motor, and this is a spring damper which models the spring and damper effect of the gear shafts, and this is a small friction model, and that is a lossy gearbox transmission which I am using it, okay. So the gearbox has an attenuation factor of 4.6 that is given as per the data sheet of the manufacturer of the DC motor. Then this is the bearing of the gearbox, and this is the gearbox inertia, the inertia of the wheel which is connected to the DC motor, okay. The velocity actuator works as the amplifier or the gain constant of the DC motor, which I have taken from the manufacturer of the motor. The feedback of the encoder, the motor position is being taken by an encoder, okay, and gives to this particular submodel. This submodel is responsible for controlling the position of the DC motor. The feedback of the encoder is given to this submodel, and the first job of this port, that is the right motor encoder, is to collect the encoder response and attenuate by a factor of 129. So this is the same model that we have used in our previous experiment. So this will convert the encoder count into revolutions. The revolution feedback is given to this plus minus block. So this subtracts by this motion profile set point which is coming to it, okay. So we could have given a constant value like 1, 2 or 3, okay, but here I am using a motion profile which will give a step or the clock kind of profile to the position of the DC motor. By subtraction of these two values you get the error value, and that is given to an PI controller, which is a proportional integral controller, and the output of this controller is given to the input of the DC motor from this port. So this is the submodel that we would be downloading this. There is a signal limiter in between, that is to protect the output of the PI controller going more than plus minus, so that the model do not goes, or the motor do not goes by the over limits. You can always go inside the controller models or any of the submodel in the 20-sim and understand how the equations are being written and how do they work. The left motor is connected to a dummy value of 0, so that the left motor remains static and do not disturbs the main right motor, okay. So that is the simulation model on this. So this is a mechanical model, okay, and this is the controller model that will be downloaded in the hardware. So let's start simulation. So this is how the simulation we get. The blue line is the set point of the position control, and the pink line is the simulation output of the DC motor position control. So here you can see that as I'm using a PI controller, so he follows the blue set point closely, but not that very closely, but that's okay. That is the learning part of the PI controller performance, that how does it work. You can always change the motion profile values by going in the parameter block and going in the submodel, click on the motion profile. You can always change the stroke values, like for example instead of 1 revolutions you want 2 revolutions, okay. So here you can see that it will go take 2 revolutions and try to control it. Okay, you can reset it and run the simulation again. So this is how you can see this. So to get the same performance in the hardware, you have to make sure that your hardware description of the motor setup has to be accurately matching the real-time setup or the real-world setup. Let's test this model and see how does it works in the real world. So go to Tools, Real-Time Toolbox, C Code Generation. Select the 4C toolchain template and select the sum model, balancing board position controller PI, and click OK. So you will create the project folders. So this opens the 4C toolchain. Select the target template at the balancing board. Click on Apply. Go to Connect block. So for the input we have the right motor encoder input coming. So we connect to the right motor channel. On the output side we have the left motor. So select the left motor, and the right motor we select the right motor. Make sure you do that correct, otherwise things will work in a different manner. Just compile. So go on the command block. So you can change the finish time as 10. You can change it if you wish, or otherwise let it be like this. So run for 10 seconds. So we will run this with logging so that we can record what is coming at the output. So you can select the variables which you want to record. Here is the complete list of variables, or it's better. I go on the motion profile and select the X and check the flag log. Then I go to encoder to rev motor, that is the attenuation block, and select the output. And here you can see the counts are values set to 129. Okay, if you want you can even select the PI control output to see that how does it works. Click on Apply. Okay, and let me show the model to you. So here we have the bot. I have kept it upside down, so you have to also ensure that you keep it upside down. So here you can see the rotation of the wheel, and I bring it on the left, and run with the logging. So here you can see that it runs 2 rotations clockwise and come back anti-clockwise 2 rotations to its original position. So here you can see that this is how the rotation takes place. Okay. So here this is the profile. The blue one is the actual response, and the pink one over here is the motion profile response, and the red one, this is the PI control output. Okay. So this you can see that this is very closely matching our simulation data. If you want, you can go back to performance, like you can change the motion profile stroke value back to 1 and see it running and run again. So with the screw you can make it reference that this is how it's running. So there you can see that it runs in the exact manner of the simulation plots. Now you can see change the values of PI controller. For example, the gain is 0.1 instead of 0.5, make it 0.1 and see how does it works. So here you can see a little offset is there. So the controller takes slow responses and goes overshoot too much and again overshoot too much from the main performance. So the same stuff you can see from the controller simulation over here. So this is my 20sim simulator. I set the same values over here. I make it the stroke as 1, and the PI controller instead of 0.5 I make it 0.1 and run the graph. So here you can see that I also get the same responses. So this is the same response, okay, which we get in the hardware. The only that there is a flat line, okay. Yeah. but you can see the deviation is the same. Okay. So this is how you can do the position controller executing in the real world, giving the performance, okay, in the hardware. Okay. The users can play around the various kind of controllers and see how they perform. Okay. So this will be the end of this experiment. Thank you.